Hello everyone, this is mechanics of materials. Okay, in this video I'm going to show you the exercise for the support reaction. Okay, because how to calculate the support reaction is also the main topic in this course. Okay, support reaction. Okay, calculate reaction from the support. Okay, so suppose, okay, here's the problem. Suppose we have a beam here, and then here is AB support, and here it said A is a roller support, and B is a pin support, and it's being also subject to the external load, and it's also distributed load. Okay, and it's calculated, and this problem want to calculate the reaction from the supports. Okay, there was a reaction force from the supports. Okay, and okay, so we start to get this problem. And for example, so first of all, we just draw a free body diagram of this problem. Okay, first of all, just draw a free body diagram. Free body diagram. Free body diagram, that means free body diagram means it's free from surrounding. Okay, so there's a pin here. So free body diagram. Okay, so I just treat the pin as a very thin rectangular. Okay, and then we have AB support, and A is a roller support, so it only has the support reaction force upward, right? And we call it AY. Okay, if you don't know this, you should check the previous slides. Okay, previous slide we have talked about the pin support only have upward reaction force. Roller support. A is roller support. Roller support only have upward reaction force. And then for pin support is allow the rotation, so it doesn't have any reaction moment, but it provide the reaction force upward and horizontal. It provide horizontal and vertical reaction force to the pin. So because this the pin supports, it doesn't allow any translation in upward and vertical direction and horizontal direction. So there is a reaction force from the pin support. Okay, and roller support allow the translation on horizontal. So okay, horizontal direction. Okay, so the support from the B, I call this upwards BY, and horizontal is called BX. Okay. This is not, that's kind of very bad. Okay, I think I should draw the B. It's not BZ. Sorry. BY is here and BX is here. Okay. And the other thing remaining is okay, we have this being subject to the distributing loaded. Okay, for distributing loaded, all we need to do is, okay, for the free body diagram, I just want to draw this the one resultant force. Okay, and know its position. The position is called X bar. Okay, so in this when the calculate okay, so the next thing is we have to find the magnitude of distributed load and where is the position of this distributed loaded. Okay, so this is 6 meter. Okay, the resultant force, magnitude of resultant force is just area under the distributed curve. Okay, this the area under the distribution curve. Okay, so for the distribution curve, okay, so it's a trapezoid. Okay, so it's a trapezoid. Okay, so the area of the trapezoid is very easy. 10 plus 30 times 6 divided by 2. That's your force, resultant force. So it will be 120 inches is kilonewton. Yeah, and we just note its direction is pointing downward. Okay. Okay, so that's the resultant, the magnitude of resultant force. And where is the resultant force? Where is the resultant force? So we have to use the moment balance. Okay, and before simplification, after simplification, and before simplification. Okay, before simplification, we need to draw another diagram. to calculate the moment before simplification. Okay, and then right now our reference point is A. Okay, okay, here is 10 kilonewton. Okay, here is 30. So okay, this is 10. So here is 20. Okay, and we need to know because trapezoid is complicated, so we divided the trapezoid into a rectangular shape and rectangular shape and a right triangle shape. And then with these two simpler shape, we can find the resultant force and the resultant force of each area and the centroid of each area. Okay, and then we use the moment balance to find out the position of the final resultant force. Okay, so this is 6. Okay, and where is the centroid of the rectangular? I believe it's here. Okay, where is the centroid of the right triangle? I believe it's here. Okay, and I believe this must be 3. Okay, and this distance must be 6 divided by r 3 over h, right? 6 over 3. Okay, equal to. Okay, just convince yourself this is the conclusion of the centroid of right triangle, and I don't want to explain this anymore. Okay, this should be a basic knowledge in the mechanics of materials. Okay, so and then we have a resultant force for area 1, I call FR1, and the resultant force for area 2, FR2. Okay, and what is FR1 and FR2? Okay, it's the same. The resultant force is just equal to the area under the curve. So area for FR1 is area of rectangular. So it's 10 times 6 is 60 kilonewton. Okay, 60 kilonewton, right? 10 times 6. Okay, 10 times 6, 60 kilonewton. Okay. The kilonewton and downward. Okay, FR2 is area of this triangle. It's 6 times 20. 6 is here, 6 is here, and 20 is here. Don't forget this is 20. And divided by 2 is also 60. Yeah. And it's also point downward. Okay, and then we use the A have a reference point. A has a reference point. Okay, and before simplification and after simplification, yeah, the moment, the moment with respect to the A must be the same. Okay, and after simplification, well, okay, resultant force Fr is here and X bar. So that's Fr times X bar. Okay. And in this problem, I just make a convention. I just make a sign convention that the clockwise is positive. Okay, just make this convention because I don't want to write negative sign too many times. So I just in this problem I call clockwise is positive. Okay, that will make the equation looks neat. Okay. Okay, so FR. Okay, so our reference point is A. So FR1 times 3. Okay, here is FR1 times 3, and it's clockwise. Okay, and I especially assign the clockwise as clockwise is positive. Okay, and here's FR2, and what's the distance? What's the lever arm for FR2? So and it's also clockwise, so I think it's positive. So FR2. And what's a lever arm? Okay, FR lever arm 3 is easy. FR2 lever arm, which is lever arm. So here is 2. So this distance must be 6 minus 2 must be 4 because here is 2. Okay, here is 2. And I don't want to explain this, just convince yourself. Okay, so here is 4. So this is 4 here. And FR1, okay, we already know 6 times 3, FR2 60 times 4 equal to FR, we already know FR is 120 times X bar, so X bar is, I think it's 3.5 something. Yeah. Yeah, 3.5 something. Okay, so we finally get the position resultant force here is 3.5. Okay. Okay, we finally got our the position of resultant force. Okay, and then we can figure out we can determine the reaction from the support and using the rigid body equation. Okay, but before that I need to clean this up. Okay. Okay, for rigid body equation for rigid body statics. Okay, statics. Okay, static rigid body and statics. So summation fx is equal. I think this problem we can treat this as a two-dimensional problem. Okay, because we ignore one dimension here. Okay, this looks like it's two-dimensional problem. Okay, and rigid body and statics. Don't forget the rigid body and statics. Okay, okay. Some resultant force equal to 0, x direction equal to 0, y direction equal to 0, and your moment. And this problem, our moment, reference point. I just used A as a reference point. Okay, some A is equal to 0. Okay. So let's start with the resultant force in x direction must be 0. So x direction we only have bx, right? Bx equal to 0. Okay, I think that's the answer. And y, okay, we have ay point upward, by point upward. Okay, ay plus by, and we have a resultant force point downward. Okay, so resultant force, what's the maximum resultant force? Or 120. Okay, minus 120 equal to 0. So you will get ay plus by equal to 120. Okay. And the final one, resultant moment at a reference point, okay, is 0. Okay, in this one, okay, just okay, the force at A, okay, the force AY doesn't create any moment because there's no labor arm. Okay, convince yourself. And okay, and the resultant force FR, yeah, this force create a moment with respect to A, so it's 120 times 120 times 3.5, and in this equation we back to the normal convention, so it's clockwise, so we have the normal convention. Okay, 100 minus 120, and then here for the B, okay, bx, okay, because the force B, this force doesn't create any moment because because there is no level arm, but the by create a moment with respect to the point A. Okay, point A. So it's upward and reference axis is here, reference point here. So it's create counterclockwise. So it will become positive by times 6, and all the moment here must be 0. Summation must be 0. Okay, so from here you will get the by equal to, okay, I think I can erase here. You will get a by equal to what? Okay, let's use a calculator. By, okay, divided by by is 70. Okay, very good. By is 70, and 70 units kilonewton. Okay, if we get a by, because ay plus by is 120, so we will get the ay is 50 kilonewton. Okay, and we already get a bx, so we got the 3 reaction force from support. Bx 0, by 70 kilonewton, and ay is 50 kilonewton. Okay, so this is a very typical problem. So for the calculation of the reaction from the support, and this is also a key point of this course. So I just make another video for more exercise for such problem. Okay, because in maybe later in the shear moment diagram, yeah, you still need to do this calculation again, very similar calculation again, and then draw a shear moment diagram. But we will get there, and okay, we'll talk about shear moment diagram in the later of this course. Okay, I just finished a video here, and see you in another video. Bye bye.